we have 4x squared plus 12xy plus 9y squared. Now we have a bunch of extra variables here, but it seems to that it will fit our area, because if we put 4, well, first of all, is there a greatest common factor? There's no greatest common factor. And if we put this into our area, 4x squared, 9y squared, these terms are going to be x's. I have x's here, y's here to get the y squared, and we should get xy in here. So it looks pretty consistent. So I'm going to go ahead and just factor it normally. So again, since we have a coefficient in front of that x squared, really we would help ourselves out by multiplying that first times last. So that's the same as multiplying along this diagonal. So we get 36x squared y squared. And we know that the middle term 12xy, we have to split that up into two groups of xy terms, and they have to add to 12 and multiply to 36. Well, that's a fairly easy one, because a perfect square of 36 gives us 6xy here, 6xy here, and that diagonal then multiplies to 36x squared y squared. So there I have my area all arranged in the proper places here. So I'm going to go ahead and find the common side lengths along here, which is 2. They share an x. Here is going to be 3, and they share a y. Vertically, it's going to be 2, and they share an x. Here, it's the same thing. It's going to be 3 and share y. In fact, it's perfectly symmetrical. And since it's squares on these sides, we know that we have actually a square shape. So we end up factoring this into the area 4x squared plus 12xy plus 9y squared. The area factors to side length of 2x plus 3y, 2x plus 3y. And since it is a perfect square, we can write this as 2x plus 3y squared. Okay, so since it is a square shape, this will end up being a square shape. We can write it as square. However, we can leave it as multiplication as well. And just a warning again, if I want to apply the square, I cannot do it with a plus and minus. So if I want to work this out, I actually have to use times and go back to that form. So just practicing our general factoring, the very first thing we always do is factor our greatest common factor. So we check along here, the greatest common factor is 7, and I have a common x as well. That leaves me with x squared plus 2x plus 1. I have to check if that's factorable. Are there two numbers that multiply to 1, add to 2? Okay, I have to remember to bring that factor with me, because that's still part of the expression. So two numbers that multiply to 1 and add to 2 are 1 and 1. And since this is the same factor, it's a square, we can leave it like that, or we can express it with a square. So here we have to check for greatest common factor. Well, there's no greatest common factor here. This one looks a little bit hard to do because we have a leading coefficient of 64. So this could be a problem. We could do our box here and say we have 64y squared and a z squared here. But since this is the x squared, or sorry, z squared and y squareds are symmetrical anyways, I could just rewrite it like this. As long as I keep track of my pluses and minuses here, really I'm just looking for two numbers that multiply to 64, and these two add up to 16. Well, I know that's going to be 8 and 8. So I'm going to end up with, well, it's got to be negative 16. So it's going to be negative zy, negative 8zy. So this factors to z minus 8y and z minus 8y. Okay, so if we just look at it from a different perspective, we can actually just factor this as a leading coefficient of 1. If not, we can still do the same thing here, right? We have our diagonal product of 64 z, y, and so it's going to be negative 8 and 8, so I end up with 8y minus 8z, sorry, minus z, and I have 8y minus z, okay, which is actually the same thing. Okay. And the reason why these are the same, because to make this switch around, I need a negative 1 here. Well, that means it's different, but I would do the same here to switch these around. And that negative 1 times negative 1 factor actually works out to be positive 1. So these end up being exactly the same. So either one of these is perfectly fine. Here we should recognize that 4, power 4, power 4, well, those are actually squared squareds. So we can use a difference of squares and use our conjugate pairing. So I have square root plus square root minus square root. Okay, well, this is not factorable. Okay, so this is not factorable. Remember, these are two squares. We can't arrange them in a rectangle. Okay. However, this does still factor, so we need to continue factoring. So we end up with x squared plus y squared, which is not factorable. That is still a difference of squares, so we can factor to its conjugate pairs, x plus y, x minus y. Here we have power 4, power 2 in a linear term. Well, that doesn't look like a quadratic, but in fact, if we rewrote this as x squared minus 10, instead of x squared, we can just think of it as 1 power of x squared and plus 9. This is really x. If we just ignore the red x squared, we can just think of this as x squared minus 10x plus 9. And we can just factor like this. So I'm looking for two numbers that multiply to 9 and add to negative 10. Okay, so that's going to be negative 1 and positive negative 1 and negative 9. So it looks like this. So I'm going to say that I'm going to do the number parts first. So I'm going to have negative 9, negative 1. That's going to give us a positive 9. And the leading part of that is going to be just x squared. Okay, so when I multiply this out, I get x squared times x squared gives me the x4. I end up with 1 x squared, negative 9, negative 1x squared, negative 9x squared, which gives me the negative 10x squared, and then the 9 and 1 gives us the 9 plus 9 here. So I've now factored a power 4 into two power 2 polynomials. Now, I'm not quite done because this is still a difference of squares. So this factors to x plus 3, x minus 3. So that's what we have to recognize, that once I factor, this is actually a difference of squares. And this as well is a difference of squares here. So I can factor that into x plus 1, x minus 1 into its conjugate pairs. Okay, and if I'm not sure about this, I can always just multiply this all together, and you'll see that although it's complicated, we're going to end up back to that power 4 polynomial.